Welcome all to this session, which is going to be the last one for describing curvilinear motion using the cylindrical coordinate system. I would like to tell you that this section 12.8 is going to be described in two parts. So this is the beginning of part 1. So our objectives are to distinguish between cylindrical and polar coordinate system. Then we will define radial and transverse direction, which are a new direction or new axis. And then we will describe the angular velocity as well as the angular acceleration. Cylindrical motion is either observed or guided from the origin or from the center. Whenever we have a three-dimensional motion, we can describe it by cylindrical components r, theta, and z. If we have a motion which can be described in two-dimension space, we call it planar motion or plane motion. Then we used polar components, which are only r and theta. So these are two simple real-life applications in which we can use cylindrical or polar coordinate system to describe the motion. In this one on the left, we have a car moving over a curved path, and we can basically identify the motion or describe it by a vector from this origin all the way to the car as it moves over this circular path. And we can see here that this can be described by theta and a vector r. So this is a plane motion, which we use polar coordinate. But if we have an example like on the right hand side, the car here is moving over a spiral path or rod, so it's not enough to describe the motion just in terms of r and theta, but also in terms of z, which is the elevation over here. In this way, we use cylindrical coordinate. So let's start with polar coordinate. In polar coordinate, basically, what we have a particle which represents an object right here, and moving over a path which is shown here with the blue line. Now, if we want to use polar coordinate, then we need to construct a radial direction, which is shown here by this vector r, and we need to have a transverse direction which describes the rotation, represented by theta. Now, the line which is going from an origin pointing toward the particle is basically the radial direction, which is represented by a unit vector ur. Now, once we define the radial direction, all what we need to do is to construct a line perpendicular to it, which is going to help us construct the transverse direction. So transverse direction point toward the direction of the rotation, while the radial direction point toward the position of the radial position from the origin of the particle. So theta is usually measured in radian, and don't forget that 1 radian equals to 180 degrees divided by pi. Okay. So based on what we talked about just in the early slide, we can express the location of the particle P in polar coordinate system as r, which is equal to magnitude r multiplied by unit vector ur. But you have to note that the radial direction r extend outward from the fixed origin, which is right here, and the transverse direction is measured counterclockwise from the horizontal. So this is indeed the positive or the sign convention. So as far as the radial direction is pointing in the direction of the particle, then this is considered to be the positive direction, and counterclockwise is the positive transverse direction. Now, a little hint over here. Unlike NT system, the normal tangential coordinate system, there is no guarantee that one of the coordinate directions will be tangent to the path. And I think this is very clear over here. As you see, the path is right here. But if I show the two axes of the coordinate system, one of them is here, the other one is there, and clearly there is no tangent. Now, let's describe the instantaneous velocity using the polar coordinate. We start with the velocity vector v, which is equal to the time derivative of the position vector r. And because we know that the position vector is defined as the magnitude r multiplied by the unit vector ur. Now, here again, similar to the normal tangential system, the unit vectors rotate and they move with the particle. So we need to be very careful. The derivative here has to be applied to both the magnitude as well as the unit vector. So this is going to give us r dot ur plus r multiplied by u dot. So the question here, again, we know that this is the rate of change of the position vector, which is going to be the velocity. And this is just a unit vector. Here, this is the position. But what is the derivative of the unit vector? Now, we can use the chain rule to try to understand what is the derivative of this unit vector. So this is dur over dt, which is equal to dur vector by d theta multiplied by d theta divided by t dt. Now, clearly, d theta over dt is very simple. This is just the rate of change of the angular position. So indeed, what we are going to get here is theta dot multiplied by dur over d theta. Now, we will have to find what is this part of the derivative. Now, similar to the normal tangential system, we can have a derivation to prove that dur over d theta is actually equals to the unit vector u theta. But I'm not going to go through it. You can go check it from the textbook. But if this is what we get, then the part dur over dt is going to be theta dot multiplied by u theta. Therefore, we will have the velocity vector equals to r dot ur vector plus r theta dot u theta vector. Just to remind you here that this r came from the equation that in the previous slide, v equals to r dot ur plus r ur dot. So all what we did over here is that we proved that ur dot vector from here is this. and we substitute it back over here. That's it. We can rewrite the previous equation of the velocity vector v, which is equal to r dot ur unit vector plus r theta dot by u theta unit vector as vr by ur unit vector plus v theta by u theta unit vector, which are basically the radial and the transverse component. And if we look at the schematic on the right hand side, we can see that this is the radial direction and this is the direction of the radial velocity, and here perpendicular to it we have the transverse direction where the transverse component of the velocity. Now if we calculate the magnitude v, then it is equals to the square root of r dot square plus r theta dot square. Now the total component of the velocity vector is tangent to the path. Now as shown over here, that this is now tangent to the path, but the component themselves are not. And if you look carefully over here, the angle delta in here, which is the tan inverse of v theta divided by vr, is basically the angle measured from the radial component to the total component. So if you want to measure the direction of the velocity, it's basically theta plus delta. So here, as I was saying, the angular velocity is theta dot, while the angle of the velocity is basically theta plus delta, where delta, as I showed over here, is tan inverse of v theta over vr. Now let's find the expression for the acceleration. So the acceleration vector, which is the derivative of the velocity vector, is going to be equals to d over dt of r dot ur plus r theta dot u theta. Now if you look carefully, r dot ur, r theta dot, and u theta, all of them changes with time, which means we are going to get 5 terms in the acceleration vector. So just focus with me. A is going to be equal to r double dot ur plus r dot ur dot plus r dot theta dot u theta plus r theta double dot u theta plus r theta dot u theta dot. Now let's inspect this again. So r double dot is the second time derivative of the position. So this is the acceleration. This is the unit vector ur. This is the velocity because it's the time derivative of the position. This one is something we don't know. This is the time derivative of a unit vector ur. But if we move on, this is again, as I said, this is again velocity. This is another velocity, but this one is theta dot, so this is the angular velocity. This is unit vector u theta, the transverse direction. This is r, the position. This is the angular acceleration, so theta double dot. And this one is u theta, which is the transverse unit vector. And this is r the position, this is the angular velocity, and again here we have a time derivative for another unit vector. So I'm not going to go through the derivation, but I'm just going to let you know that ur dot is equal to theta dot u theta, and u theta dot is equal to minus theta dot ur. So now if we substitute this, we will get the acceleration vector equals to r double dot minus r theta dot by ur. So this is the radial component of the acceleration, plus, let me write this one in black, we have r theta double dot plus 2 r dot theta dot by u theta. So this is the transverse component of the acceleration, which is, we're gonna see it, this is it, and this is the radial component. So from the previous slide, we have shown that acceleration can be actually written as ar by ur plus a theta by u theta. And what ar is equal to r double dot minus r theta dot square, while a theta is equals to r theta double dot plus 2 r dot theta dot. So again, this is the radial acceleration, which is pointing over here, and this one is the transverse acceleration. If we want to find the magnitude of the acceleration, then the magnitude is going to be equal to the square root of r double dot minus r theta dot square all squared plus r theta double dot plus 2 r dot theta dot square. Now, what you should know is that this acceleration is not necessarily tangent to the path. So you will get that the component of acceleration, one of them is here, the other one is here, and this is the total acceleration. And we already described this many times. And what is remaining over here is the angle. So if we want to find phi, which is the inverse tangent of a theta over ar, then we will see that this angle is basically found by, if we measure this angle over here, then it is the opposite, which is a theta, divided by the adjacent to the angle, which is ar. But if we want to find the direction, the angle of the acceleration, then it is basically theta plus phi. So it is not enough to measure. So this is measured from x-axis, which is this angle plus this one. Here we reach the end of part 1 of section 12.8.